Thank you for the introduction. Hello everyone, my name is Shanto Rahman. Today I'll talk about our research, understanding and improving Flaky test classification. Flaky test is a test that can pass or fail non-deterministically when running the test many times. Let's assume we have a list of tests that are running in CI/CD environment. Oh, okay, sorry. Extend. Okay. Okay, thank you. Okay, sorry. So Flaky test is a test that can pass or fail non-deterministically when running the test many times. Let's assume we have a list of tests that are running in CI/CD environment. So when we run the test, at the first time we find that test 4 is failing, and then in the next run no test is failing. In the next run we again find there is no test failure happens, and then when we run nth time we find another test, which is test 3, is failing. So this test 3 and test 4 are known as Flaky tests. So Flaky tests are very bad because developers very frequently lose their trust on the test suites. So Flaky test is everywhere. Google, Apple, Microsoft, BMW, Meta, they all report that Flaky tests hurts their CI system. What a Flaky test is? So here is an example of Flaky test that is taken from an open source project, and here we see that in this test at line 5 a thread object is created, and then at line 9 it is checked that if thread object is still alive. So the expectation is that that thread will no longer alive after this 1500 milliseconds. However, the problem happens if the thread could not finish its executions within that time. At that case, test failure happens. So what makes the test flaky? So there may have different reasons why a test is flaky. For example, async await can be one of the reasons why a test is flaky. Concurrency, time, order dependence between the test, unordered collections are the root causes why a test is flaky. Now the question is, why do we care about knowing the root cause of flaky test? So it is important to know the root causes of Flaky test because we can directly apply the repair strategies to that type of Flaky test, because prior studies shows that to repair any specific category of Flaky test, we first need to know the category of the Flaky test. Now the question is, how can we know the Flaky test categories? One possible way can be manual inspection. However, manual inspection is very time consuming. That is why we might rely on a classifier that can predict the category of the Flaky test. Here the expectation will have a classifier, and there will be a test that we want to send to the classifier, and the classifier will tell us the category of that test. In this paper, we have two major contributions. The first one is Flaky test classifications, and the second one is understanding the classification model. Now I'll talk about each of the steps one after another. First, investigation of existing Flaky test classifiers. Flakify is one of the popular and prior state-of-the-art technique that predicts if a test is flaky or not. We ran Flakify to classify input categorize multiple categories, and we find that the macro F1 score is 81.82. However, when we look at the Flakify implementation, we find a major critical bugs, and we find that when they load the bug is in during the loading the codebart model, it happens that each of the fault they reuse the previously fine-tuned codebart model instead of reloading a fresh pre-trained model. As a result, data leakage issue occurs because a test can appear in a training set of one fold may appear in a test set of another fold. And after fixing this issue, we find that the F1 score goes down to 56%. We report these findings to the Flakify authors, and they acknowledge our contributions and they updated their code base. And then we also look at their evaluations, what are the datasets they consider to evaluate their techniques. We find that in existing technique, that is Flakify considers 5.5 times more flaky tests than the non-flaky tests. Another technique, which is FlakyCat, that contains only different category of flaky tests. There is no presence of non-flaky tests. However, in reality, we see that flaky tests are rare. Google report that 1.5% tests are flaky. Microsoft found that 4.6% of their tests are flaky. So here the question comes, then if we do some training on unrealistic dataset, then our model will be biased. Hence, we propose FlakeBench, which is a realistic flaky test dataset. Here our main goal is to increase the number of non-flaky tests. So that's why we start with all the projects that FlakyCat dataset contains, and we collect all the unlabeled test methods. Then we run each of the tests 100 times, and we consider each test as a valid one if we don't find any intermittent failures. And finally, we got 280 flaky tests, which is only 3% of non-flaky tests. And this also indicates that our data is highly imbalanced. So to work with this highly imbalanced data set, we propose a new fine-tuned model that can classify if a test is flaky or not, and also the category of flaky test. Here in our experimental design, we enforces the project-wise disjoint split instead of stratified k-fold cross-validations. And during model training, we also enforces the strategy so that it can handle the high imbalanced data set. For example, here we consider focal loss instead of cross entropy loss. We also use L2 regularization to give more penalty on the higher weight. Now our research question comes. Here we first look at how flaky lens perform on FlakeBench dataset, and then we also look at we also compare our result against the open source generative language models. So here we see that when we fix Flakify, we find the result goes to 56.62, and our flaky lens can achieve 65.79% F score, which is 9.17 percentage point improvement. And when we compare against the open source generative language models, we find that our technique Flaky Lens performs the best for all category of flaky tests. Now, once we get a comparatively better model, now our main investigation point is what makes a model to make some decisions. Hence, we consider these contributions, that is understanding the classification model. Here I am again bringing back the initial example that I showed, and this test is an asynchronous flaky test, and we find that our model that is Flaky Lens can correctly predict the category. However, like now we want to know what are the tokens that are getting more importance. Hence, we calculate the token importance. To calculate the token importance, we measure the integrated gradient, confidence score of the model, and also how many times that token comes across different tests. And based on that, we find the attribution scores per token, and we find that for this test, we find sleep is the token that is getting maximum attribution scores. For the details, please see our paper. So here we see that what are the important tokens. Can we make some generalization per category? So here we see that here we include top 5 tokens per category. These are the most important tokens, and we also report the least important tokens. We see the attribution scores for the most important tokens are very high compared to the least important tokens, which are close to the 0. Now, we are interested to really know, like, are these important tokens actually impacting the predictions. So hence, we apply the data perturbations, and in our settings, data perturbation is works in a way that we change the code, test code, but without changing any semantics of the code. Here we apply 5 different types of data perturbation: date code, print statement, and 3 more. Here's an example how date code data perturbation works. So here it is clearly clear that this code block will never be executed because it's a while false block. And then, however, still we see that when we inject this data perturbation, our model predicts this test as a time category instead of async weight. So the reason is very clear because there are lots of tokens here that contains the time keyword. So now we want to see like how what is the impact when we consider it on per category. So is it still happening in all the tests or how the result drops? So here we see that when we apply the data perturbation considering the most important tokens, we find the accuracy drops 18%. And then when considering the least important tokens, it drops 8%. And also the minimum one is the 8.32, but when you consider the least important tokens, it is only 1.76. So it clearly indicates that when we are considering the most important tokens that have the most effect in making the predictions. So in conclusion, in this paper, we built Flakebench dataset that considers a more representative mix of flaky and non-flaky tests. And we present Flaky lens, an improved flaky test classifier. We identified important tokens based on the attribution scores. We confirmed that their impact actually matters in making the decisions. Our code and repositories are available here. And on a side note, I would like to mention that I will be in the academic job market this year. I'll be happy to chat more about my research and for the future collaborations. Thank you.
Thank you for the talk. We have 2 or 3 questions before we can go for the coffee break. So,
hi, I'm curious. So I might have missed it on the slide, but is there a possible category of a flaky test where it seems like the test itself isn't the cause of the flakiness, but actually the system under test? So like, let's say that there's a data race going on,
yes.
but it's really subtle.
Yes. So the question is like, if the test can be flaky because of the code under test? Or?
Yeah, so is it able to classify, so you're classifying tests are flaky because the implementation of the test itself is flaky?
Yes, yes.
So what if there's like flaky behavior in the system under test?
Yes, yes, it can happen, especially like the example that I'm showing, the thread is waiting for few milliseconds to finish the other task, for other threads to finish its executions. So most of the cases it happens that that thread is waiting on the code under test to execute its task. But the problem happens if the test and that code under test is not properly synced. In that case, the test becomes flaky. Yes, that can happen.
Right. So like the solution there would be to like change the test, right?
Change the test, or like we have one paper before where we introduces the synchronization between the test code and the code under test. So we collect some systematically analysis and we find that location where to add the synchronization between the test code and the code under test.
Right. So like what happened? Is it able to classify like there's not an issue with the test, but the thing that you're testing actually has a data race. So you're having a flaky test that happens to find an issue every once in a while, but it's a legitimate bug that it's finding. So is it able to categorize that, or is that like kind of something that it can't find?
Yes, so if it happens that there is no problem in the test code, but still it is a data race issue, our test, and if it does not observe in the output, like if the test failure does not happen, then we are not considering as a category.
Okay, so that was just my question. Yeah, thanks.
Okay.
Hello. For these important tokens, which I guess correspond to different methods that people use to write their tests, are we able to just ban them and write all of these tests using other methods that avoid all this flakiness? Like, can you create a linter using the tokens you've identified and to reject them?
So that's a very interesting and good question. So once we know that, okay, these are the tokens that can make that test flaky, for example, thread.sleep. So that's like we want to make developers aware about that okay, this type of uses of thread.sleep can make the test flaky. So instead of doing that, we encourage the developers to use some other technique, for example, synchronization between the test code and the code under test, or some other, for example, thread dot yielding, like, or some other things that, so that this specific weighting we can overcome. So that's the key point we investigate. That's the reason we investigate the tokens things.
All right, thank you.
Okay.
Thank you.
Thank you.